Okay. So let's talk about how visible light and how X-rays are different. So now I've done a bunch of work today to describe to you how these things are the same, right? How visible light and X-rays are kind of the same thing. They're an electromagnetic wave. We talked about how they're made from the oscillation of moving electric and magnetic fields and the electrons, and they travel all at the same speed. So like X-rays and visible light travel at 3 times 10 to the 8 meters per second, right? There's a bunch of similarities with them, yeah, but there's a bunch of differences too. The wavelengths of the light make it so they interact differently with different types of matter. That was one thing we've already said. So let's characterize them, how they're different. Visible light, which is just like all the other electromagnetic waves, a double transverse wave, but with different energies, penetrations, transmission, reflectivity, and refraction characteristics from other types of light, other types of electromagnetic wave. Visible light follows the laws of reflection, okay? X-rays do not. X-rays are not reflected by a mirror. They penetrate right through the mirror with slight attenuation. The mirror stops some of them, but they don't bounce off the mirror, right? Visible light follows the laws of refraction. They can be bent when passing through an interface. They can be focused. If you wear glasses, you're taking advantage of this right now, right? The visible light goes through your glasses lenses and is bent a little bit before it gets to your eye's lens. That corrects for the error of refraction that your eye was built with, right? X-rays are not refracted by a glass lens. They pass right through it in straight lines. So X-rays travel in straight lines, or they don't travel at all. The law of reflection is that the angle of incidence is equal to the angle of reflection, or either angle of reflection is equal to the angle of incidence, right? So if I take a ball, so if I take a ball and I throw it straight at the wall, I'm standing perpendicular to the wall. Every time I throw this ball at the wall, what can we expect? It's going to bounce straight back at me, right? Even if I can't catch it. Okay. But if I stand at an angle to the wall, right? So let's say I'm a 45-degree angle to the wall. What will I expect when I throw the ball at the wall? Will it bounce back at me?
Probably hit me.
Maybe hit you, maybe hit Joe. Let's see what happens. Right? If you play pool or billiards or whatever, you know this, right? You know that the angle of incidence is equal to the angle of reflection because you angle your pool cue, right, against the ball, right? And you find that right angle to bounce the ball off the wall and to the other pool ball, the other billiard ball, right? The one you want to hit. So yeah, if you're standing at a 25-degree angle to the wall and you throw the ball at the wall or hit the pool cue at the wall, it's going to bounce and exit that at that same direction, right? Same angle of reflection. Visible light works like that, right? So if you're standing in front of a mirror, you can see yourself. But if you're standing at an angle to the mirror, you see kind of what's over on that side of the room, right? You don't see exactly you don't see yourself, for example. You know this because the mirrors in your car, you angle them correctly so that you can see things that are behind you, right? You go get in someone else's car and you have to change the position of their mirrors to reflect the light in such a way so where it gets to your eyes and you can see it, right? If somebody's way taller than you, you have to move the rear view mirrors around a little bit. We use this in the X-ray tube all the time. You know, you turn on the X-ray collimator light and there is a light projected down to the table. Well, if that light bulb were put like right in here, if that light bulb were just placed right here to shine down towards the table, it would get in the way of the X-ray beam, okay? So what we do is we place the light bulb off to the side and we put a mirror angled at 45 degrees. Now the light bulb sends light out to the mirror. It hits the mirror at a 45-degree angle and it bounces off the mirror at a 45-degree angle. But the mirror is angled at 45 degrees to the table. So what happens is the light starts here and makes a 90-degree turn downward towards the tabletop. So we can project light down towards the table using a mirror. But the X-rays from the X-ray tube just pass right through that little mirror. Okay, a little bit of absorption, tiny bit, but they pass right through that mirror. Visible light refracts. As it travels through a medium, it bends. It doesn't go straight through the medium. So like a light coming out of a body of water, right? When you look into like a creek or swimming pool or whatever, you look down and see something that's down at the bottom, it's not where it looks like it is, okay? It's in a different location because the light is bending as it travels through a medium. This is just like light traveling through the lenses of your eyes too. You know, it takes time for you to focus on things when you're looking at it, right? X-rays don't do that. By the way, the angle of incidence is not equal to the angle of refraction like it is for reflection. Notice how the light came in at a 15-degree angle to the surface, but it's now exiting the other side at a 25-degree angle. There's a relationship between the amount of refraction according to the medium that we're traveling through. We're not going to learn any of that. Okay, we're just going to learn that refraction is the bending of light as it passes through materials. Dispersion, the orderly splitting of white light through a prism into several colors. This is something that Isaac Newton first accomplished. He took and he shined a source of light, which he had, what was the primary source of light for people in the 1600s? Candle, or same source of light that we have now. Sun, right? Candle or sun. So he used sunlight in this case because sunlight was not known to have any extra colors in it, right? Sunlight was sunlight, right? Yellow sunlight. But he took it and he ran it through a triangular shaped thing called a prism, and he split up the light. He showed that light is actually made up of these different colors: red, orange, yellow, green, blue, indigo, violet, which is indigo and violet are just purple, okay? Newton had some special attachment to numbers, and the number 7 was a special one for him, so he didn't like that there was only 6 colors in the rainbow. He split up purple and made it indigo and violet. Funny stuff about Newton. Diffusion or scattering, the random refraction or reflection of light, destructive to any image, but light scatters. You can put, I can shine this light through here and have it kind of spread around the room, right? It spreads and diffuses and scatters all around the room as I shine it through that bottle of water. Absorption. Visible light can be absorbed by many, many things, where X-rays pass through things. Absorption. Transmission is the complete passage, right? The complete passage of a source of light without any loss of energy or intensity. Our next term, these are just some terms getting down on the board. Attenuation. Attenuation is an important term. Well, where X-rays do not reflect or refract, they are attenuated. X-rays are absorbed, visible light too, but X-rays are absorbed partially by things that they pass through. They pass through things, but they are absorbed by things too. Some of the energy of a single incoming X-ray, or some of the intensity of or quantity of X-rays within the beam, is partially absorbed as it travels out of the X-ray tube through the matter that it interacts with. Some tiny percentage, single-digit percent points of the original beam are passing through the body and exiting the other side of the body. This property of what we call differential attenuation allows for the formation of images. Think about it like this. If all of the X-ray beam was absorbed by the body, we couldn't make any X-ray images because it just would make an outline of the body, right? Like visible light does. You cast a shadow, right? You cast a shadow because the visible light's not passing through your body, okay? So we'd make shadows, okay? If all of the X-rays passed through the body without absorbing it all, then we would not be able to make any images, okay? It's this partial absorption of the X-ray beam called differential attenuation that allows us to create X-ray images, okay? The different ratios of absorption and transmission characteristic of each different tissue in the body. Different tissues absorb things differently. How many different tissue, or what different tissues can we demonstrate on X-ray?
You mean like organ tissue?
Yeah, what? How many? 'Cause we can't show everything, right? Can we show bone, muscle, fat, gas? Yeah, you can show 4 different tissue densities. That's going to be in the muscle category, but liquid. So we'll put bone, liquid, fat, and gas, right? Good. So 4 different densities, right? And if you include like metals too, because for foreign bodies or prostheses, things like that, you can include those. So 5, right? Okay. That's because X-rays absorb differentially in different tissues, and they absorb different for all different tissues, but we can see roughly these 5 different tissue categories. Terms like radio-opaque and radiolucent are opposites of each other. If something is radio-opaque, it does not permit X-rays to pass through. If something is radiolucent, it permits X-rays to pass through. The sponges we use on our radiographic tables are radiolucent. In fact, our radiographic tables are radiolucent because we put the Bucky underneath the table, or the cassette in the Bucky under the table, right? You don't see the table, okay? Radiolucent. If you've ever used a lead blocker or a gonadal shielding, those are radio opaque because if they ever show up on the X-ray, they appear pretty much bright white, right? Same with the metals in patients' bodies. Positive and negative images are positive image is dark details against a light background, which is not typically what we have. Usually we have a negative image, which is a light detail against a black background. So when we go to negative on our X-ray images, it's actually positive because we start out our image as negative. When we see the white bone, black background, that's actually the opposite of what's true. Okay, it's just easier on the eye to start with like that, and so that's what we use. Okay.